I think they count the verbal double, and because there's a new writing section.
Oh, okay.
Yeah. When I took it, that's what it was.
Yeah. Okay. Yeah. I was like, I was reading. I was like, I couldn't get past that part. I was like, I got better score.
Okay. Basics of hypothesis testing. Last time, at the end of class, I tried to fill you in with why you might want to do this and what these things were. We defined a hypothesis last time. It's a claim about a property. So I could tell you, I could make a claim about the mean, or a claim about the proportion. I could say, here's a claim. More than 50% of the students who take statistics are female. More than 50% are female. What do you think about that claim? You'd say it's accurate? You'd say more than 50% are female? Show of hands, people that are female? We have, let's see, 5, 6, 7, 8. Show of hands? How many are in the class? Right? That's because I want to know the proportion. So let's see. I have 10, 15, 16, 17, 18, 19. I got 8 out of 19. So let's see what I just did. The claim, what was my claim? More than 50% of stats students are female. And then what I just observed, what was it? How many females again? Let's double check. 8 out of 19. Do you think I counted that right? Okay. 8 out of 19. Now, by the way, is 8 out of 19 more or less than 50%? Less. Could my claim be correct? Because I'm making a claim about what? Yeah, a population, a huge population. There's a lot of people across America taking statistics, right? This is a convenient sample. That's right. Okay? So we've talked about the pluses and minuses of using convenience samples, right? But if we ignore that for the minute, okay, and I say I have a sample, then I guess the question is, would this observation say anything about the claim? David? We have a lot of people missing. But do you think females take off more than males? Are you saying something here, David? Okay, don't get yourself in trouble. Let me ask this. What if we looked at the class and we said only 4 out of the 19 were females? What would you think about my claim then? Do you think that might refute the claim or not? How many say yes, that would refute the claim? How many say no, that would not refute the claim? I mean, what if I had 0 out of 19 in my class? Does that refute the claim or not? Well, definitely we have to say not necessarily, right? I mean, and that's one of the reasons we've been talking about confidence intervals, right? Because I say I'm 95% confident that this is true about the population, but you can't be 100% confident, thank you, because you may have a really bad sample in a sense. When I say bad, not representative of the population. You have to keep that in mind, and that's why we talk about confidence intervals. Now, we're going to talk about how to test claims like this today. How we do it statistically. And that is the goal of today's class, is that you walk out of here able to test a claim like that from a sample. Okay. There it is. The main objective of the chapter is to develop the ability to conduct hypothesis tests for claims made about, well, a population proportion, P. I'm going to start with that today. or a population mean mu. We'll do that on Thursday. And I'll even touch upon standard deviation on Thursday. We've kind of ignored that for a week and a half. I want to bring that back. Kind of saved him for last because he's a little different. But in some ways, he may be the most important. So, oh, we did all this. I gave you millions of examples of why hypothesis testing may come into play. Okay. But here's a slide you've seen before. I put it back in again. The rare event rule for inferential statistics. If you get an observation that's exceptionally small, we conclude what? That maybe the assumption is not correct. Yeah. Sure. Let's see if I can give a nice example of that. Suppose I think that the mean age of let's say of statistics students is 14. Now, that'd be a dumb thing to think, probably, but, you know. Then I could take, you know, our sample here. I could ask everybody's ages. I don't want to embarrass people, but we're going to, if we did that, we could compute the sample mean, x bar. Now, what do you think the sample mean might be if we took everyone's age in here? Don't you think it'd be like in the 20s somewhere? 22, 23. You do throw the mean? All right, Shelley. Let's say it's 22. I don't know. But let me ask you this. Do you think that, you know, what I could do now is I could look at a confidence interval around my sample mean, right? So I would have 22 plus E, and I would have 22 minus E, right? And I would know that mu has to be in there. With how much confidence? Well, remember, the more confidence you want, what does that mean about the interval? If I want more confidence, so we've been using 95%, right? But if I ask for 99% confidence, the only way I'll get that is to make the interval larger, right? Okay. So suppose you pick some interval, 95% or 99%, and you compute your error. Let me ask you this. Do you think 14 is going to be in those confidence intervals? It might not, right? So if I pick a 99% confidence interval, and if 14 is still smaller than this, then what would you say about my hypothesis? You're wrong, yeah. Now, are we guaranteed my hypothesis is wrong? No. Maybe there's some classes of 7-year-olds taking statistics in this really advanced college, you know, that, but do you see what I'm saying? This is an example, okay? Sure. Okay. So now I'm going to give you what are the components for a formal hypothesis test. Now, the way our chapter is structured, it's kind of like last chapter. We're going to start off, just introduce it. Here's what hypothesis testing is. And then we'll go through proportion, and then next time we'll go through mean and standard deviation. So that's the structure. Now, the first thing I need to teach you about is what's called the null hypothesis, H naught. It's a statement that the population parameter you're going after. So what are we going after today? Proportions. Proportion is equal to some claimed value. The null hypothesis has to be that the proportion is equal to something. Equal. See that blue? the null hypothesis you're going to have equal to. Matter of fact, the example I gave, I said that the mean age was equal to 14. That could have been a null hypothesis if I went through the whole formal thing. I didn't yet. Yeah. Nope. Not for the null hypothesis. Okay? Well, okay. Wait and see. Wait and see. There are going to be two hypotheses. When we do a hypothesis test, though, what we test is we test the null hypothesis. Okay? You're either saying we have verified the null hypothesis or we did not verify the null hypothesis. Okay? That's what you're testing. Here's the two conclusions, in a sense, that you can get, although you won't state it this way. You'll actually speak English when you're going to give an answer. This is the stats language. Reject the null hypothesis or fail to reject the null hypothesis. In the made-up sample that I didn't actually do, I said my null hypothesis might have been the mean age of statistics students is 14. But maybe I can reject that claim after I do some stats. Does that make sense? Okay.
And then if you find out that it is 14, you fail to reject it?
So the interesting thing is, I won't be able to prove it's 14, will I? Unless I had all the population data, but you're not going to. I can prove I can either say it's not 14, or else I can say I wasn't able to say it's not 14. It's kind of strange. Kind of strange. You have to see some more examples before you'll get it. So give me a second here. Now, along with the null hypothesis, we're going to have an alternative hypothesis, H1. So I will show you an example to show you how this works. But first of all, what is it? The alternative hypothesis, and we will call it H1. Some books call it something else. H8. Actually, not just books. Some of you guys, when you get into your field and you start doing statistics, you might see HA someday. Just remember, that's the alternative hypothesis. But everyone uses H0 for the null hypothesis. So this is a statement that the parameter has a value that is somehow different than what the null hypothesis said. It's kind of like, okay, we're going to test the null hypothesis, but here's the alternative. You're going to use these symbols, guys. I didn't have to write all this. I could have just written this, what I'm circling right here. We're going to use not equal to, or greater than, or less than when we talk about H1. Let me go back to H0 for a second. What symbols do you think might come into play for H0? Equals for sure, right? Because that's what we said, is you have to be saying you're equal. You are also allowed to do this for H0. You're allowed to do less than or equal to, and you're allowed to do what? Greater than or equal to. So let me just show you an example. If I had a null hypothesis, suppose my null hypothesis was P is less than 0.2. Suppose I had that. Can you tell me what? Oh, wait a minute. That's no good. I just did it wrong. I can't use that for a null hypothesis. Why not? I don't have an equal to sign. Now, what can I do? Less than or equal to. I can do that. Okay? So when I'm setting up the two hypotheses, please make sure that H0 does allow equality, because that's what makes it the null hypothesis. Okay, what do you think H1 would be? It has to be an alternative. P is greater than 0.2. Do you see that, Kristen? So I guess we're going to see that there are different kinds of tests you can do. Left-tailed, right-tailed, and two-tailed, and I'll get to that. Yeah. Yeah. So I guess the important thing is that it contains equality. It doesn't have to just be equal to. You could have one like that. You could have, suppose my hypothesis is that the population equals, I'm sorry, the proportion equals, let's say, 0.75. Well then, what would be H1, the alternative hypothesis? The proportion does not equal to 0.75. You keep the same numbers when you do the two hypotheses. The only thing you change is what? The signs. Okay? Scott?
The alternative, it could be any other plane besides the H0, or is it just
You want the complement. You want the complement. That's right. Wonder why they don't call it the complement. I don't know, but they don't. Yeah?
So, like, for the first one you wrote down, you couldn't be less, B is less than.
No, because it's less than or equal to, so then the alternative would be greater than. Yeah, let me write that down. That really what we're doing is a complement here. I didn't see that in anything I've read, but that's really what it is. So we'll have to come back to that maybe. So that it becomes the alternative hypothesis. Okay, let's see what this means. How do I support a claim? And the answer is make it the alternative hypothesis. Now why? Why is that? Well, because remember, I said what it is that we're testing. We test which hypothesis? We test H0. And either we reject H0 or we fail to reject H0. Okay, so this is a little confusing, so I want to go through it slowly. Yes. If I fail to reject H0, I learn nothing. Really? Well, it depends if you're an optimist or a pessimist. If you're an optimist, you say, well, that's kind of cool. But if you're a pessimist, you say, I didn't learn anything. Because you really didn't. You failed to reject something. You failed. But if I reject H0, what does that mean about H1? Wait a minute. If H0 is rejected, so we get that H0 is false, what does that mean about H1? H1 is true. Right? H1 is supported then. So again, this is kind of abstract, but if I can reject something, then I can support the alternative. Yes, Scott.
So you always start by looking at H0. You can't start with the H1?
Well, I'll show you an example in a second here, but if you are trying to support something, supporting a claim, make that H1. If you're trying to, because what we're going to do is we're going to test H0, and maybe we can disprove H0. Supported. Well, let's see an example. Let's see an example. This is a little checklist that's in your book. Let's skip that for now. I want to find an example. Here we go. Remember the problems we had with ergonomics when they were talking about the weight of things, and we did this in the other chapters. But this particular example is kind of nice. It's from your book. consider the claim that the mean weight of airline passengers, including their baggage, is at most 195 pounds. Follow the three-step procedure outlined in Figure 8.2, in other words, in that figure I just had, to identify the null hypothesis and the alternative hypothesis. Okay, so what's the claim? Claim is that the mean weight, well, what's the symbol we want for the mean? Mu. And it says is at most 195. So what do I write? Less than or equal to 195. That's the claim, right? That's the claim. Watch the procedure. Step 1. We say mu is less than or equal to 195 pounds. I just did that with you, right? That's the claim. Step 2. If mu less than or equal to 195 is false, what's the complement of that? Mu is greater than 195, right? These are complements. Does that make sense to people? Oh, okay. Because if I'm equal to, I'm part of the claim, right? You can't be part of both. So if this one already has the equal to, which it did, because we said at most, that includes being equal to, then the other claim is this one. Well, let's see what we do here. Now, of the two, we see that mu greater than 195 doesn't have inequality. So you're right. We're going to make this guy H1, and we're going to make this guy H0. And we can test this claim. Mu is less than or equal to 195. Oh, I'm sorry. Yeah. There's two claims, right? Mu less than or equal to 195 pounds, or mu greater than 195 pounds, right? Now, notice that this being false is the same as mu greater than 195 being true, right? These are complements. What is it we want to test here? Back here, major correction. Okay. H1 can use any of these symbols. H0, we're only going to allow you to have equal. No. Has to be equal. Yeah. Well, no, I guess not. So that's why they don't use complement. Remember I said, I wonder why they're not using complement? Well, that's why. Okay. Yeah, sorry about that, but at least now we got it straight. But only use equality. Let's go back to the example from the book. Okay? It does. So, okay, so let's talk about this, right? I mean, we want to say, is mu at most 195 pounds, right? That's what we want to say. Okay, so what's the complement of that? The complement of that is this. And the nice thing about this one is that notice there's no equality here, right? And there is equality here, but this can't be used as what? as H0. Can't be used as H0 because, again, what I wrote before was wrong. You have to have, so let's figure out how we do this. Yeah, not H0. We can't do that. This can be used as H1, but H0 is going to be mu equals 195 pounds. This is what we're going to test. And yeah, that makes sense to me because of how we're going to test it. There's going to be 3 different ways we can test it. We are going to test this statistic. We think, what if mu equals 195? Okay? And if we show that that's no good, maybe that'll support our claim that mu is greater than 195. That's kind of the idea. Okay? And now here's the big note. It says, note, the original claim was mu less than or equal to 195, right? Is that the null hypothesis? No. Is that the alternative hypothesis? No, because it had equals, so that was no good. It's just the original claim. We'll be able to say something about the original claim when we're done with the hypothesis test. Yeah. All right. I'm going to stop here, let you take that break. Now, I have to show you how to do the hypothesis test. And I will. And it's going to be, you're going to say, oh, we've done that before. Okay, so it won't be too bad. But once you do the hypothesis test, you have to make a decision. And the decision is, do we reject the null hypothesis or not reject the null hypothesis? That's the 2 things you're allowed to do. So the next thing I'm pointing out here is that there are different ways to decide. Different methods, if you want, to decide. And you'll read about this when you do the reading. The first method is called the p-value method. Using the significance level alpha. Hey, we've seen that before. What's the alpha we've been using most often in this class? Yeah, it was the 2 tails, and what was it? What value was it? We kept using alpha is 0.05. Why? We were constructing 95% confidence intervals, right? So this is an example of what alpha can be. Okay? So our book and most statisticians nowadays use something called the p-valued method. And notice I'm using capital P. That's because we've already used lowercase p for proportion. I don't want you to confuse them. But the capital P value, it's going to be a value. And if it's less than 5%, we're going to reject the null hypothesis. Right? Or if it's less than whatever your alpha is. If it's greater than alpha, well, we don't know anything. Okay? How do you remember that? Oh, do I want to do this yet? Okay, this is a second method. I want to wait a second on that. Here. The best thing to do is to look at an example for me to explain this. So could you look at example 2 from this section? We already looked at example 3. They get 14 couples to do the XSort method. That's a lot of money right there, right? Times 3,000 each. 13 have a girl, 1 has a boy. Okay. We want to say, is this going to support their claim that you're more likely to have a girl or not? See, and there's big stakes here, aren't there? So that's the question. Can we support the claim? So how does this testing go? How do we do the hypothesis test? Well, okay, before I show you the graph, let's kind of walk through a little bit. So we assume that the population P proportion. That's my proportion, right? What do you expect the proportion of girls to be? Yeah. 0.5, right? That's lowercase. Yeah, thank you. That's lowercase. So now, instead, if we say XORT is effective, it's going to improve your chances. We could express that as P is bigger than 0.5, right? Does that make sense to people? Okay, so this is my claim, right? By the way, which is going to be which? Yeah, this is the null hypothesis. It's the equality. And this is going to be the alternative hypothesis, right? And you'll notice that they're kind of lucky here because you want the alternative hypothesis to be the claim you're trying to support. Yes, Kristen? Yeah, so you have a choice. You can do three different things. You could say we want to claim that P is greater than 0.5. You can also claim that P is less than 0.5. And you can also claim that P is just not equal to 0.5, meaning greater than or less than. These are three different approaches. Well, let me ask this. What does XORT want to claim? They want to claim that it's going to be more likely that you get a girl. So that's why they use this one. It's by context, yeah. I guess the point is that you'll be able to use any one of these. And we're going to have different testing techniques for each one of these. So I'm glad you're asking that. That's the. Let's just do them one at a time. We will test one of these claims as the alternative hypothesis. In this example, I'm doing P is greater than 0.5. Okay? So, what happens? Well, it says using a normal distribution as an approximation to the binomial distribution, see section 6-6. I didn't do section 6-6 with you. I skipped it. But we have learned that a lot of times we get normal distributions, right? The central limit theorem tells us that's going to happen, etc. Fine. Let's show you the picture. Okay. Hey, it says here there's a critical value, z equals 1.645. What is that coming from? Well, that's coming from the fact that the area alpha is 0.05. What's that coming from? Okay, there's a lot going on here, okay? Let me point out a couple things. If I go back to here, you notice that this is the claim we're testing is that P is greater than 0.5. This is what you're going to call a right-tailed test. Okay? It's because of the greater than, yeah. It's the region of the graph that we care about. If we did P is less than 0.5, that would be a left-tailed test. And if we do P is not equal to 0.5, that's going to be called a two-tailed test. And by the way, the homework problem on the board, that picture where I have 2.5% here and 2.5% there, that's the kind of picture you'd get for a two-tailed test. Okay? But this is a right-tailed test. And here's the idea. Well, we need to pick what we want to use for alpha. Now again, 95% confidence interval, we could actually construct that if we wanted, right? That's one way to go. That corresponds to alpha being 5%. Right? Amber, you with me on that? Are you with me on that? Okay. You look funny at it. I was like, okay. I just made up 95. I don't see it in the book. Okay? But if we do that and we look at the picture, okay? Because this is a right-tailed test, the critical region, meaning where things go bad in a sense, is here, the right 5%. See how it says alpha equals 0.05? We want this right region to be 0.05, 5% of the total area. Does that make sense to you guys? Yes? 0.025. That's right. That's right. Now, this is called the critical value. We've done this before. You guys know how to get the z-value, right? How do I get the z-value? Inverse norm of what? Well, of 95, sure. Because that'd be the area of the blue, and then you'd find the z-value. Kristen? I just gave it to you just now. Okay? We can change alpha if we need to. I don't see it in here. I guess if I go back to... no, I don't have it. Okay. Oh, because don't we do areas from the left? And how much of this blue is there? 0.95, right? Because this is 0.05. You don't put it in a z-score in inverse norm. You get a z-score, right? That's going to give me the 1.645. Yep. Okay. So far, so good? Now, what's that? I'm not looking for 0.95. I knew it, because if this is 0.05, that's got to be 0.95. That's what Shelley just asked. It's because that's how I find the z-score. So we're still having trouble finding z-scores. It's how do you find the z-score on a normal distribution? Well, you know the area. So either you use the chart, that's the hard way, or you type in inverse norm of 0.95, and it'll tell me 1.645. And that's what we did. Alpha was 0.05, so what's left over is 95%. Okay? Yes, Kate?
How come the grade book says z-score, like the area is 95%, z-score is 1.645, like you get, but the critical value of 1.645 is only a confidence level of 90.
That's because in the back of the book, they're doing a two-tailed test when you look at that. This is a one-tailed test. So if we had a two-tailed test, we'd have another 5% over here. Okay? That's a good question. This is the first time I can think of that I've shown you a one-tailed test. Okay? So. All right, now. The next thing it says on this little screen here, I'm going to point out, it says that p hat is 0.929. Where the heck did they get that? Well, I think I know. Try your calculators and tell me. Weren't there 14 couples that were tested? And weren't there 13 that had girls? Try that. 13 divided by 14. That's the population proportion, or that's the sample proportion, right? Okay. So now what you do is, let's find what's called the test statistic. Oh, and we haven't seen that yet. Okay. So hang on a second. In section 3, so in section 8.3, we will use the formula. And I guess I'll write it up here. I don't know. Let's see where it is. It should look pretty familiar, actually. Well, not exactly. It's close to what you had before. It's going to be this. Z equals p hat minus p over the square root of p q over n. Boy, that does look a lot like what's on the board. Not exactly, though. Not exactly. But in section 8.3, when you guys are working on that homework, we're going to have to use this formula. P hat minus p over the square root of p q n. All right. Yeah, I want a calculator. Show you how to do this. There's my calculator. What do we type in? Well, let's see. We need p hat. So what are we going to type in? 0.929. Subtract what? Well, p, that was the population we assumed that we would get, 0.5. See? What you're doing here is you're trying to figure out, hey, how far away is our sample proportion from the actual proportion? Well, there it is. And now we need to divide by something. We need to compute the square root of PQ over N. So let me compute that. The square root of, now what's P? 0.5. What's Q? Q is also 0.5. So remember, P and Q have to add up to 1. Divided by, now what's N? 14, because that's the size of my sample. All right, so here is some crazy decimal. The square root of 0.5 times 0.5 divided by 14. Okay, so I'll take my 0.429 and I'll divide by that number. Enter. I got 3.21. Good. That's where they got that test statistic. Okay. So I guess I'm, hinting at the next section as I do this. But that's okay. Yeah?
How is the test statistic useful?
That's what I have to go over now. Okay? The idea is that if you have a critical value, okay? Well, let me explain this. The traditional method did the following. In the traditional method, what you would do is you would look at, well, where is z equals 3.21 on the picture? That'll be way out here somewhere, right? Z equals 3.21. Is that in the critical region? Yeah. So if that happens, we would reject the null hypothesis. This test statistic, you really have... So the traditional method was see if the test statistic is in the critical region. I have this written out elsewhere. In that red. Yeah, that's right. That's right. No, if it's in the critical region, you want to reject the null hypothesis, okay? As a matter of fact, here it is stated right here. For example, see the red region in the previous figure. Let me go back to it. See, 3.21 is in the red region. So we're going to reject the null hypothesis. What was the null hypothesis? I'll have to keep straight. H0 was that P equals 0.5. Remember that? That's right. That's what's called the traditional method. Okay? That's the traditional method. The other method we're talking about is called this capital P value method. And I'll have to do a slide that'll show you that. Significance level, I mentioned this. Yeah, you guys asked me, why did I pick alpha's 0.05? That's a common choice. Sometimes you'll use 0.01, sometimes you'll use 0.10. But that's called the significance level, alpha. The critical value, that's the Z thing that we found, right? So we understand that. You don't need all these words. Yeah, but that was that Z equals 1.645. That was the critical value. I labeled that for you. Okay, now here I should be a little careful to show you what's going on here. P value. The definition is here, the probability of getting a value at least as extreme as the one we got. If I go back to that example I had, what was P hat? 13 out of 14? 0.929. Okay. So here's my question. What is the probability of of X being bigger than 0.929? I'm not X, I guess P. Little p. Try that again. What is the probability that little p is bigger than 0.929? That's what we're going to call the P value, capital P. It's the area to the left of the test statistic. Because we had, or I'm sorry, in our example we had a right tail. It'd be the area to the right of the test statistic. Let me go back to the picture and show you the P value. Okay? Now, here we are, guys. There's the test statistic, right? See this black I'm shading over here? Is that a lot of area or a little bit of area? That's a little bit of area. That would be my capital P value. Okay? If I get a capital P value that's small, that means I'm in the critical region, and that means what? Reject the null. Reject the null hypothesis. That's right. Here, let me say it for you. The null hypothesis is rejected if the P value is very small. Here's a nice little poem that might help you remember it. If capital P is low, the null must go. If capital P is high, the null will fly. I didn't write that. I didn't see it in the book, but it's a nice poem. I didn't show you, I'm sorry, go ahead.
So capital P is higher than your test statistic?
No, you get capital P from the test statistic. I didn't show you how to compute capital P yet. I did explain what it is. It's the area to the right of that statistic. But the thing is, I think you guys know how to compute it. Because it's a normal distribution, right? Sure. Here. No, it's not always to the right. Depends if you're doing a right-tailed test or a left-tailed test or a two-tailed test. We want to go towards the extreme, right? So in the example I just had, wasn't Z equal 3.21? Wasn't this the test statistic? Okay. So we want the area to the right of that. So how do we compute Well, the probability that z is bigger than 3.21. Okay, this is something else we went over today. If I know the z value, because I computed that already, here's where I computed 3.21. And I want the area of the black. What do? Well, let's press second distribution. What am I going to use? Normal CDF. And I want from 3.21 to what? 10's good enough. Yeah, I mean, something really big. Okay, what is that area? Oh, it's small, right? So that means my p-value is low, so the null must go. Yeah. I think the XOR, we can safely say what? What is it we can say about XOR? When you use XOR, we can reject H0, right? Which said what? P is what? 0.5. So if we reject H0, we conclude what? Well, H1 is true, right? But you don't want to give that as your final answer because, again, you're explaining to the people in your paper that you're writing about XOR, let's say. What is it you want to conclude? We conclude XOR works, right? Better than 50% of the time, yeah. Better than 50% anyway. Right? It has to. It's just too unlikely that we would have gotten 13 out of 14 if XOR didn't work. How unlikely is it? We actually computed how unlikely it was. That's our p-value. That's how unlikely it is. 0.0006 is how unlikely it is. Way less than 1% chance that we just got that kind of a sample if it didn't work. Okay? Know the difference between capital P and little p. I'm going to move on. Okay. What are the tails? I already mentioned this. They are the extreme regions, right? Oh, I guess I didn't say, when will you use a two-tailed test? Do you know? When you're doing the not equal as your alternative. That's right. And I think I have a couple pictures here to show you. Yeah. So if you have H0 is equal, H1 is not equal, that's a two-tailed test, right? The alpha gets divided equally, just like we've always done. So if alpha was 5%, what do? You make the tails 2.5%, right? And if you end up in either of the critical regions, we reject H0. If you end up here, okay, we can't reject H0. That make sense? Picture-wise makes sense? I mean, it's not an example. Yeah. The picture is we have a situation here now where we have a two-tailed test. That's not the example I showed. I showed a one-tailed test. But if your alternative hypothesis is that H1 does not equal, we take alpha, which, remember, it was 0.05 for us, and we split it up into two tails, 0.025 and 0.025. By the way, what would be the critical values? You guys probably have this memorized now. 1.96 and negative 1.96. Okay? And then you do your test statistic. And if your test statistic was negative 4, you'd be out here, right? You'd reject H0. If your test statistic was 1.5, you couldn't reject H0. If your test statistic was 2.1, what would you do? Reject H naught.
Fail to reject when it's one of
Yeah.
But that doesn't make sense because if you reject it, that means you're wrong. But if you fail to reject it, then that means that you're
Well,
right.
but here's the deal, though. If I reject H naught, what does that mean then we learn will be true? H1, the alternative. If you don't reject H naught, I didn't learn anything. Yeah, it doesn't tell me anything in a sense. And you'll see the book gives you some more charts to help you with that. Kristen?
So for very much, where is the answer that's like
Yeah.
that means that the H null is correct, right?
No, it doesn't mean the H null is correct. It just means we didn't have enough evidence. I mean, maybe you'll go back and get more evidence later and test again, and then you'll say, okay, now I can reject H naught.
Is that when
That meant we rejected. Yeah. Shelley?
we fail to reject? Is that when we really don't learn anything?
That's right. If we're in the blue, we fail to reject, we didn't learn anything from that test. So that happens a lot. Then you can't conclude too much, no. Similar picture for a left-tailed test. We already saw the right-tailed test, right? If it was over here in the left-tailed test, and notice, it's kind of nice, less than. When H1 is less than, you're pointing to the left, so that's when you're going to get a left tail. I don't know if that helps you. Right-tailed is the picture we had already. Okay, conclusions. We always test the null hypothesis, right? The conclusion's one of the following. Reject the null hypothesis, or, what's the other one? Fail to reject. That's all you can do with hypothesis testing. You can't do more than that, well, with what we're doing. If the p-value is low, then what? Yeah, we reject H naught, right? If the p-value is higher than alpha, then fail to reject. The traditional method was, hey, look where that test statistic is. In the critical region or not. And that's fine too. Another option that we already learned about. Oh no. Well, yeah. And this is done sometimes. They'll just tell you what the p-value is. And maybe they don't tell you alpha. Right? So say I told you, hey guys, the p-value for this problem was 3%. Would you reject the H naught or not? Well, if alpha is 0.05, would you reject it? Yeah. But if alpha is 0.01, would you reject it? No. So I guess that's the question. Is 0.03 low or not? Well, it depends on your standards, I guess. Sometimes we'll leave that to the reader. And don't forget about confidence intervals. This is another thing you can do, and we've done it, so we'll continue to work with those. Yeah, I'm about out of time. This is in your book, a nice little checklist of how to word the final conclusion, and you'll get practice on that as you do the homework. But please don't put this on your homework. Don't make this the final thing you write. Reject the null hypothesis. No, don't do that. Write something in English that tells me you understand what you just did, what you just proved. Accept versus fail to reject. All right, guys, we are out of here. If anyone wants extra help, I'm free till 2 o'clock.